Welcome back. Today we will be talking about optimization, which involves techniques that lie at the heart of many of the most important applications of differential calculus. You may want to maximize something like profit or minimize something like energy. And the way that calculus comes into the problem is very simple. If we have some function f, and we want to figure out how to make its value as high as possible or as low as possible over some interval, we are generally considering hilltops and valley bottoms like these. This point right here at the bottom of this valley is what we would call a local minimum. If you move a little to the right, the value of the function goes up. If you move a little to the left, the value of the function goes up. So we're locally at the minimum. It's not a global minimum, because if we go far enough to the left, well, we go up and then eventually come back down and reach values that are lower than where we started. But locally, it is indeed a minimum. Similarly, this point here would represent what we would call a local maximum of the function. Change the input by going left a little bit, and the value of the function falls. Change the input by going right a little bit, and the value of the function falls. This is as high as you can get, at least locally. And in fact, on this interval AB, it looks like it's the global maximum as well. We also see on this graph that we have another local minimum here, and that one happens also to be the global minimum, where our globe, so to speak, is this interval from A to B. All right, well, if we have some function f and we want to find these points, find the values of the input that bring us to those points, how do we do it? Well, we discussed this briefly in the last video. The one thing that these all have in common is that at each of these points on the graph, there is a horizontal tangent line. And this is where the calculus comes in. If we're looking for places where the tangent is horizontal, that's equivalent to saying that we're looking for places where the derivative of this function is 0, since the derivative measures the local rate of change, the local slope. So to find the local maxima and minima, what we do is, of course, to solve the equation f prime of x is equal to 0. Solving that equation for x gives us some set of points. In this case, this equation would have 3 solutions, here, here, and here. And once we have found the solutions to this equation, we can usually just follow our noses to figure out how to optimize the function. But this is the core of it. To find the various local maxima or local minima, which collectively are often called the local extrema, to find the local extrema, we set the function's derivative equal to 0 and go from there. A couple little things I should point out at the outset. One is that this basic technique can miss some things. For example, if we had a function g that looks like this, and we wanted to find its local extrema, well, obviously this point right here is a local maximum, but if we find g prime of x and set it to 0, we're going to miss this point because this function does not have a derivative at this point right here. It doesn't have a derivative because locally this graph is not a straight line. It has that sharp corner. So no matter how closely you zoom in on that thing, it will not look like a straight line. It just looks like a corner. And as we learned long ago, differential calculus breaks down at corners. So this technique has to be used with a little bit of care. If you have places where the function doesn't have a derivative, you have to bear that in mind and think about them separately. One other way in which this technique could fail to deliver points that we're actually interested in would be if we had a graph that looked something like this. If, say, h represents profit, and we're trying to maximize our profit, and we went about solving the equation h prime of x equals 0, well, we would pick up on these 2 local extrema, but we would miss out on the fact that the way to optimize this function, the way to maximize this function, would be to let the input be b, one of the endpoints of this interval. Putting that in makes the function's value as great as possible. Well, why would we miss that when we solved h prime of x equals 0? Well, once again, the derivative here is not 0. In fact, strictly speaking, the derivative doesn't even exist at this point, because if we were to look at an infinitesimal neighborhood of that point and blow it up, we would get something like this. It's not really a straight line. It's a ray. It only goes in one direction. It's possible to define such a thing as a left derivative, but we're not doing that here. But even in that case, this isn't horizontal. So even if we did define such a thing, we would miss it when we were searching for candidates with that equation. All right, I say these things as a warning in the beginning, just because I want you to keep your wits about you and remember that you have to use your brain and not just calculate blindly. For the most part, though, we will be looking at cases in which solving this equation, where the derivative is equal to 0, will get us where we want to go. There's one last thing I'll mention before we jump into an example or two, or three. The solutions to this equation, f prime of x equals 0, are sometimes called the critical points of f. I like to think of the critical points as reasonable suspects. After all, if I'm trying to find local extrema of f over some interval a to b, well, there are infinitely many real numbers in that interval a to b. When we solve this equation, we narrow our list of possible suspects down from an infinite number to just a handful of critical points. And sometimes, based on the situation at hand, we may need to throw in endpoints or places where the derivative isn't equal to 0. But as I say, that's the exception to the rule, but something to keep in the back of your mind. Oh, one other thing occurs to me. Not every critical point corresponds to a local extremum. I'll give you a very simple example. Consider the function g of x is x cubed. Well, if we wanted to find the critical points of this function, the first thing we would do is to take its derivative, which is 3x squared. Now this is 0 only when x equals 0. That's the only critical point of our original function. So we might think, oh great, we found a critical point. Is it a local maximum? Is it a local minimum? Well, it's neither. Think of the graph of this function. When x is 0, right here, yes, we do have a horizontal tangent, like so. But that is just because we have a very brief, momentary flattening of the function. It's not a local maximum, of course, because if I move this way, well, the value gets higher. And it's not a local minimum, because if I move this way, the value gets lower. So this critical point corresponds to neither a local maximum nor a local minimum. So some of our suspects can go free after we think about them a little more. Okay, and now I think we're ready to move on to our first example. Let's suppose that we are designing a can, an ordinary metal cylinder that might contain soup or beer or peas or whatever. Suppose we're designing a can whose volume must be 1 cubic meter. Well, that's a big can, so it's probably not going to have soup or beer or peas in it. But anyway, we are in charge of designing such a can. And our job is to find the dimensions we should make it so as to minimize its surface area. So here's the optimization. We're trying to minimize something. Now, the first bit of advice I want to give you with problems such as this is don't begin by writing down equations and things like that. Just take a few minutes and think about the thing. Consider the situation you're dealing with and just screw around with it. By doing that, you'll start to get a feel for the problem, so you have some intuitive sense as to what's going on. So let's do that here. We want a can whose volume must be 1 cubic meter. Well, that's our constraint. The volume is something we don't have any choice in. It has to be 1 cubic meter. Well, what is it that we can change? Where's the play in the joints? What little knobs can we turn to get different sorts of cans? Well, the only real parameters here are the radius of the can and the height of the can. If you tell me I've got a cylinder and the radius is such and such and the height is such and such, well, then I know what cylinder you're talking about. I know what can you're talking about. And I may have drawn the can with fairly conventional dimensions, but there's other ways I could change it. For example, I could have a can where the top and bottom have a very small radius. But if I shrink the radius, the only way I can keep that volume the same is by compensating by increasing the can's height. So I might end up with something like some tall, skinny can, which has maintained the volume of the original one. Or, of course, I could go the opposite way by increasing the radius, like so, and therefore I'd have to compensate by shrinking the height if I want to keep the volume at 1 cubic meter. So maybe I would end up with something like this. And of course, you can imagine all sorts of intermediary stages between these, or more extreme versions. I could take this one, this can that looks like a hockey puck, and do a version in which the radius is much bigger than that, and therefore the height is tiny, like this. That's what I'll have to do if I want this giant radius, but I maintain the constant volume of 1 cubic meter. Or I could take this direction to extremes and end up with some ridiculously high can with a tiny, tiny radius. But all of these things will have the same fixed volume of 1 cubic meter. What we see is there's this balancing between radius and height. We can change either one we like, but when we do, the other is going to change in response to keep the volume at 1 cubic meter. And our job in this problem is to find the dimensions of the can that will minimize its surface area. So even though all of these cans have the same volume of 1 cubic meter, they can have wildly different surface areas. And in fact, one thing you can see right away by thinking about this tendency is that it's a good thing we were asked to minimize surface area rather than maximize it, because there is no maximum surface area. If we continue this trend, and we can take it as far as we like, we could have a can whose radius is miles, even light years. And we could have the volume we need, 1 cubic meter, by making the height tiny, 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 tiny indeed. But if I can make this thing so that the radius is a mile, then the top of the can has an area that's pi square miles. And I would have pi square miles on the top and pi square miles on the bottom. And then I'd have this thin little ribbon going around the side. The surface area of this thing is going to be a little more than 2 pi square miles. And if I wanted it to be 2 pi square light years, I would just have to have the can whose radius is 1 light year. So there's no way to maximize the surface area. Actually, that raises an interesting question if we go back to the opposite extreme, where we have long, skinny cans. As I get more and more extreme here, so if I have a can that's a mile high, what happens to the surface area? It's not as obvious as it was in this case that the surface area keeps getting bigger and bigger and bigger. Because even if this is a mile high, there's not much area here if you unroll that vast straw. But on the other hand, it's huge, so maybe it is going to infinity. It's not obvious at first. As we push this tendency to extremes, does the surface area go to infinity, or does it actually die away to 0? Not obvious, though we shall see soon. Anyway, I think you get the idea of what I mean by just screwing around with this problem, giving you some insights already. Now that we've got a feel for what we're working with, let's actually start solving it. I'm going to keep one copy of a general can because pictures always help. Whenever you can draw a picture, draw one. We are trying to minimize surface area, and we know that everything is dependent on the radius and height of the can. So of course what we're going to need to do is come up with an expression for surface area, an actual formula for area, because I need some function that I'm trying to minimize. So let's say that the can's surface area, which I'll call A, is given by, and now I need to come up with some expression for A. If I can't do that, then I have no hope of minimizing it. So the first thing you want to do when you're optimizing something is come up with an expression for the thing you want to optimize. Well, this is pretty easy. We just have to think about what goes into the surface area of a cylinder. Now, a cylinder consists of the disk at the top and the disk at the bottom. We know how to find the areas of circles, so that's easy. But it also has this lateral area. Now, hopefully you remember how to find that lateral area. But if you don't, I will remind you. If we take the top and the bottom of our cylinder and pop them off, we're left with a lateral area, and we can find that by imagining that we take this can and we slit it down the side, like we were cutting that with a knife, like it was a paper towel roll. And then we take this paper towel roll after we've slit it and we just lay it out flat. And when we do that, of course, we end up with a rectangle. So the surface area of a cylinder turns out to be the sum of 3 areas of shapes whose areas we know how to find. Let's go ahead and label the dimensions on the rectangle. Well, this dimension, where I have the red slit, that's just the height of the original cylinder. So I'll go ahead and put H there. But how about this one? Here it is in green. Well, where is the green back on the original one? This is the paper towel roll that's been spread out. So if I follow that green backwards, that would be this stuff, which is the circumference of the base. Well, that's a circle of radius r. So the circumference is 2 pi times that r. Good. Now I can write down the surface area of my cylinder very easily. I get pi r squared here and another pi r squared here, so that gives me 2 copies of pi r squared. And I have to add to that the area of this rectangle, 2 pi r times h. And now we have a nice expression for surface area. Please do not memorize this, only remember the process by which we obtained it. And now you might be excited and say, great, I've got an expression for the surface area. I know how to minimize this sucker. We just need to take its derivative and set it equal to 0. Ah, but there's a problem. This is a function of 2 variables, r and h, and you are learning single variable calculus. Uh-oh, are we stuck? No, we're not. As we recall from our brief period of screwing around with this problem, we know that R and H are intimately related because as one changes, the other has to change in response to keep the volume of the can at 1 cubic meter. So I should be able to express R as a function of H, or H as a function of R. And if I can do that, I can eliminate one of the two variables. And then I really will have a function of just one variable. Let's eliminate H. Let's try to write H as a function of R so that I can replace H with some function of R, and then this will all just be a function of the radius. How are we going to do that? Well, we can express H as a function of R since we know that the can's volume must be 1 cubic meter. That is, we know that, well, let's put this into symbols. The can's volume must be 1 cubic meter. Well, what's the volume of the can? That's just the area of the base times the height. And the area of the base, of course, is pi r squared, and the height is h, so we know that that must be 1. Solving for h, we find that h is 1 over pi r squared, just basic algebra here. Substituting this back into our surface area formula, i.e. this stuff, we obtain that the area is 2 pi r squared plus 2 pi r, and now instead of h, 1 over pi r squared. And we get some cancellation in here. We have a factor of pi that cancels out from top and bottom, and a factor of r, leaving us in that second term with 2 over r. Good. Now let's not lose track of where we are. And in fact, you'll note that I have written down several words. I've got phrases introducing equations and things like that. You need to do the same when you are writing up your work. And not just for my sake, for your sake too. It is very easy to lose track of where you are in a problem and what you are trying to do unless you can trace back your own thought pattern. And for that, you need some explanatory phrases. Anyway, this stuff represents the area of a can with base radius r and height h. And you'll notice that we have written it now so that it is strictly a function of r. If we know the radius, then we know the surface area. You don't have to tell me the height. This is just all factored in. That is why we went through all this stuff right here. We had area as a function of 2 variables, we eliminated h, and now we've got area as a function of 1 variable. And we like that because now we can do calculus. What sort of calculus? Well, this is area as a function of radius, and I am trying to minimize surface area. So if I want to minimize it, I want to find places where the derivative is 0. So to minimize this expression, we take its derivative with respect to r, which I don't really need to specify because, of course, I only have the 1 variable here. So a prime, what's that going to be? Well, the first term is easy. That's a constant, and this is a quadratic. So the 2 comes down, and we're going to get 4 pi r. And what about this second term? Well, the 2 is a constant multiple. It just sits there. And then we've got 1 over r. Well, what's the derivative of 1 over r? Hopefully you have that well memorized. That's negative 1 over r squared. So that means this next term is going to be minus 1 over r squared. But I also have that constant factor of 2, which stays there thanks to one of our linearity properties. And I'm done with the derivative. A prime of r is all this stuff. Now, why did I take that derivative? Because I'm trying to minimize this thing. I want to find the valley bottoms, and that is going to occur where the derivative is 0. So then I have to ask, when is this thing equal to 0? This is 0 when 4 pi r is equal to 2 minus r squared. If that happens, then this minus this is 0. Or solving this expression for r, when r turns out to be 1 over the cube root of 2 pi. I'll leave it to you to pause this and scratch out that equation, which should only take you a minute or two. Got it? Good. So this value is our only critical point. It's our only solution of the equation a prime is equal to 0. This particular radius makes the derivative of a equal to 0. That means it's almost certainly the radius we want. But let's just think about this a little bit. As I said, you have to kind of follow your nose, keep track of where you are, and just make sure everything is working out the right way. Let me make a little room for myself over here. We've said that surface area is a function of the radius. And in fact, we have that function explicitly written out as a formula right here. A couple of observations. 1. When we were just screwing around in the beginning, we said that as the radius goes to infinity, the area is going to go to infinity as well. That was when we had our can whose base was light years across or whatever, and the area grew without bound. So that means if we were looking at this graph on a long scale, eventually it would just be going up and up and up and up like that. And we had a question about what happens on the other side when the radius heads towards 0, and we got those tall, skinny cans that might be a mile high or a light year high. And we wondered what would happen to the area. Would it go to infinity or would it go to 0? Well, actually, we can tell now very easily. Look at our formula for area in terms of radius. As r gets smaller and smaller and smaller, what happens to these two terms? Well, as r is getting closer to 0, this first term vanishes, because as r gets closer and closer to 0, r squared gets closer and closer to 0, so we have 2 pi, which just sits there, times something that's vanishing. That means this whole first term gets closer to 0. So we might think, oh, maybe the whole thing's going to disappear. But that's not what happens, because as r gets closer and closer to 0, what happens to 2 over r? Well, we're dividing 2 by something tiny. If we're dividing 2 by, say, 1 over a million, how many millionths go into 2? Well, 2 million of them. How many billionths go into 2? What's 2 divided by a billionth? That's 2 billion. When r is 1 trillionth, 2 over r is going to be 2 trillion. So as r is getting closer and closer to 0, sure, this first term is getting closer and closer to 0, but this one is blowing up to infinity. So we have effectively nothing plus something huge, or maybe put it another way, something huge plus some dust hanging around at the end. Their sum is, of course, huge, which means that this graph, whatever else it looks like, as r gets closer to 0, the area goes to infinity as well. So now I know that my graph overall goes to infinity as r goes to infinity, and goes to infinity as r approaches 0. The only question is what happens in the middle here. Well, we've seen there's only one spot here. There's only one critical point where the derivative is 0. Only way that can happen is if this thing bottoms out somewhere at that particular value. So again, without worrying about the details of what this thing looks like, we should end up with something like this, where I've got a horizontal tangent line at this one point, which would be 1 over the cube root of 2 pi. So this has to be where we have our minimum value. You might say, well, couldn't it be a maximum? Couldn't it be that our graph looks something like this? And there we would have something like that, our horizontal derivative there? Why not that? Well, it can't be that, because if that was the case, then we would have a local minimum over here and a local minimum over here, and those would have been picked up as critical points. But we only had the one critical point, which means that we are actually looking at what must be a local minimum, and in fact a global minimum. So this is the radius of the can with minimal surface area. Of course, I asked for the dimensions, so we should probably give the height as well. The corresponding height will be, well, how am I going to get the height? Well, I know the radius, and I know this formula up here that relates height and radius. It gives me the height as a function of the radius. So substituting this into my formula here, I will end up with a height of this stuff, which is of course a mess. Fractions within fractions are nasty. So when you sort this out, you should be able to come up with 2 pi, all raised to the 2/3, over pi. And we can actually clean that up a little more, because I've got 2/3 of a copy of pi up here and 1 copy of pi downstairs. So with some cancellation, that leaves me with 1/3 copy of pi downstairs, and upstairs I still have 2 to the 2/3 power. And in one sense, I'm done. I could just say, all right, that's the corresponding height, full stop, and we've got it. To get the minimal surface area, this is what the radius should be, and this is what the height should be. But those with sharp algebraic eyes may notice an interesting connection between these two numbers. I've got this pi to the 1/3 power here. Well, I've also got a pi to the 1/3 power here, but I've also got a 2 to the 1/3 power downstairs. That means I could relate this very easily to that by putting a 2 to the 1/3 power downstairs here as well. I've popped in a factor of 2 to the 1/3 downstairs, and I've maintained this equality by putting a corresponding factor upstairs. I did that so that the bottom would actually match what I have right here. So I can rewrite it like that. But look upstairs. I've got 2 to the power of 1/3 times 2 to the power of 2/3, which of course is 2 to the power of 1, which is better known as 2. Ah, that's much nicer. Now I feel much happier stopping there. Because look at this pretty relationship we found. This radius, we've said, this is the radius of the can with minimal surface area, and the corresponding height will be this thing. But that height is exactly double that radius. In other words, the height we want is equal to the diameter of the can's base. So our can with minimal surface area has a very nice geometric property. Whatever the base looks like, its diameter will match the can's height. Good. And that property turns out to have nothing to do with the fact that the volume was 1 cubic meter. As long as we had any fixed volume and we wanted to minimize the surface area, you can show by the same kind of argument that the can that will do the job will have its height and diameter equal to one another. So if we were just trying to minimize surface area to minimize the amount of material we were using, we would end up with cans like that. Now, of course, if you open up your cupboard and start looking at all the cans, get a measuring tape out, you will find that they do not have that nice ratio right there, which means that they were not designed to minimize surface area. They may have been designed to minimize something else, like maybe the cost of producing it, because the material on the top and bottom might be different from what's around the side. Or it may just be that we have standard-sized cans for other reasons, and the optimal cans would not necessarily fit on your shelves very nicely. I really don't know. Okay, so much for the can. Moral of the story, we were trying to minimize surface area, so after screwing around with the problem, we came up with an expression for surface area. We had one variable too many. We were able to eliminate one of those variables by using this constraint we had on the volume. When we eliminated h, we ended up with area as a function of radius. So to minimize area, we wanted to see where the derivative of this thing was equal to 0. So we took the derivative, set it equal to 0, and we found there was only one place that happened. And based mostly on our screwing around in the beginning, we were able to reason that that one point had to be the global minimum. And once we had the radius, we could find the height using the relationship we found earlier between height and radius. Okay, let's turn to another problem. Example number 2. Let's suppose that this line represents a shoreline with water on this side and land on this side. And let's suppose at this point, P, a ship is anchored. Maybe it's a pirate ship, which is why it's a P. And the ship is 1 mile away from the shore. And I will call this point on the shore that's closest to the ship A. What's the pirate ship doing here? Well, of course, the pirate has come to reclaim his buried treasure, which is 1 mile down the road from A, right here at point R, which is even more appropriate for a pirate. Now, the ship is anchored and he can't move it. So to get from here to here, he's going to have to do some combination of running along the shore and swimming in the water. And he performs these two actions at different speeds. The pirate can swim 3 miles an hour and run 5 miles an hour, which is not bad for a peg leg. And the question we'd like to answer is, what path should he take to get to the treasure as fast as possible? And here is our optimization question. This pirate is trying to minimize time. So how should we solve this? We want to begin just by screwing around with the problem a bit before we do anything formal. That way we can develop an intuitive feel for what's going on before we get bogged down in algebra and calculus. And in fact, one thing I see I want to do already is to redraw this picture so that the relevant stuff is a little larger and I'll have more room to draw on it. I think that's a little better. So let's think again about what we're being asked here. We're asked to find the particular path that he should follow. Well, what kind of different paths can he take? Well, one obvious possibility would be for him to swim directly to the treasure. That would certainly minimize the distance he travels. Although he would be swimming the whole time, and he only swims 3 miles an hour, whereas if he runs faster. So since he's a relatively fast runner, maybe he wants to get to the shore as fast as possible. In that case, maybe what he should do is swim directly to the shore. That minimizes his time in the water, and then sprint down the shore to the treasure. But those are just two possibilities. There are infinitely many others. Some, of course, are quite stupid and we don't have to consider them, like he could just spiral around like this until he gets to the treasure, but we're obviously not going to consider that. He's obviously going to follow straight line paths. The only question is where he is going to make landfall, because he could, after all, maybe swim halfway between A and R and then run a little bit. Maybe that would be the best of both worlds. Or he could swim 3/4 of the way and run the rest. Or swim to a point 29% of the way and then run the rest. Who knows? There's still infinitely many possibilities. But we know that when we get to our solution, we'll ultimately need an expression for time. Time is equal to something. And we have some distances and we're given some speeds. So we want to think about how to relate those various things. Distances, speeds, and time. And that's easy since these are all constant speeds. We know, after all, that speed is distance over time, And since we ultimately want to minimize time, let's solve for time in this equation so that we end up with time is distance over speed. And bearing that in mind, we should be able to compute the time involved in covering any particular path. Like, let's just continue screwing around a bit. I'll do a little stuff over here that would normally be on some scratch paper. Let's pretend first that our pirate swims straight to A and then goes to R from there. How long does it take him to do that? Well, each path is a mile, we said. And in this path, the time that it takes is, according to our formula over here, the distance he covers, 1 mile, over the speed. And here he's swimming. His swimming speed is 3 miles an hour. So his time there is 1/3 of an hour, or it takes him 20 minutes to get from P to A. Once he gets there, he takes off down the beach to get to R. And on that path, the time it takes him is going to be, once again, distance over speed. He's running 1 mile, and he is indeed running. He runs 5 miles an hour, so this will be 1/5 of an hour, which means that altogether, he runs for 1/3 of an hour, which is 20 minutes, plus 1/5 of an hour, which is 12 minutes, which is 32 minutes. That's how long it would take him to follow this particular path to the treasure. Okay, but what if he followed a different path? What if he just swam straight from P to R and crawls onto shore exactly where the treasure is? Well, in that case, this should be even easier to compute because it's just one path. The time, we've said, is distance over speed. And what's the distance he covers? Well, if this is 1 and this is 1, the Pythagorean theorem tells me that distance is going to be the square root of 2. And what about his speed? Well, he's swimming the whole way, and he swims at 3 miles an hour. So that would be root 2 over 3 hours. And if you run that through your calculator and do the appropriate conversions, you'll find that's about 28.28 minutes. So a bit more than 28 minutes. That means this path, swimming straight to the treasure, is a bit quicker than this path. It saves him nearly 4 minutes, which could be crucial if there are other pirates trying to get to the treasure at the same time. But fortunately, our pirate knows calculus, so he may be able to do even a little bit better than that. Let's get rid of our scratch work here and move back to the general picture, newly enlightened by our period of screwing around. Well, whatever path the pirate might take, we know he's going to follow straight lines. That means he is going to swim straight to some point on the shore and then run down the shore. The only question is, what point? We've considered the possibilities that he lands at A and the possibility that he lands at R, but we need to consider the infinitely many possibilities in between. So on our picture, let's be perfectly general and say that he lands at some point L, where this is a variable point. He's going to swim from P to L and run from L to R. And what we saw when we were screwing around was that if I know these distances, then I can compute the time it will take him to do this, because I know the speeds at which he covers those 2 legs of his journey. He swims 3 miles an hour and runs 5 miles an hour. So the only question has to do with the distances. And these 2 distances obviously depend on how far away L is from A. That's the thing that's varying, so let's give that distance a variable name. Let's call it x. Well, that's very helpful because I can write these 2 distances in terms of x very easily. Since this whole distance from A to R is 1, and this is x, this leftover stuff must be 1 minus x. As for the length of this path, that blue segment is the hypotenuse of this right triangle, whose legs we both know. And therefore, the ghost of Pythagoras whispers in our ear and tells us that that side must be the square root of x squared plus 1. And now we're in business, because I have these 2 distances, each as functions of x, and dividing those distances by the speeds, which I also know, will give me the time it takes to travel down each stage of the path. And that's what I want, because I'm trying to minimize time. So that means I can get an expression for time as a function of x, and once I have that, I've turned it into a fairly routine calculus problem. Good, so let's do that. We want to minimize t, which will represent the total time it takes, which we can get by finding the time from P to L and adding on the time it takes for him to run from L to R. And now we should be able to write down expressions for each of those. The time from P to L along the blue path, well, that's distance over speed. We've just computed that the distance is the square root of x squared plus 1, and his speed when swimming is 3 miles an hour. And to that we have to add the time from L to R. Once again, distance over speed. The distance here is 1 minus x, and the speed while running is 5 miles an hour. So this expression right here gives us the total time it takes as a function of x. Good. And now looking ahead, I'm trying to minimize this expression, which means that I will soon be taking its derivative. I think it will be easier for me to carry that out if I rewrite these fractions as constant multiples of these things instead, like this. Anyway, we want to minimize this expression, so we'll take its derivative, because once again, when we're minimizing something, we're looking for valley bottoms, places where we have a derivative of 0. Anyway, t prime of x is going to be, well, we can take derivatives term by term because of one of our linearity properties. So starting with this term, we have a constant multiple of a third that sits there. And now to take the derivative of this, I will need the chain rule. First of all, my outer function is the square root function. So I get 1 over 2 times the square root of what? Of the inner function. That goes in there. So I get x squared plus 1, but I'm not done. I'm doing the chain rule, so I have to take the derivative of the inner function. So I'm going to get another factor of 2x, which I'll put up here. And I'll tend to the simplification later, but I still need to take the derivative of this second term. Well, here too I have a constant multiple. The 1/5 just sits there, and now I need the derivative of 1 minus x, which is, of course, just minus 1, which means that this positive turns into a negative. These 2's cancel out, so I can rewrite this stuff as x over 3 times root x squared plus 1 minus a fifth. This is the derivative of our time function, and the whole reason we took this derivative was so that we could set it equal to 0. So we will note that this is 0 when this stuff is equal to a fifth. Well, this is why you learned algebra, so you can solve little equations like this. We'll manipulate this until we get it into a form in which the value or values of x are just staring at us. So equivalently, if we want to solve this, we will clear the fractions and end up with 5x is equal to 3 times the square root of x squared minus 1. We're trying to solve x, and one instance of x is trapped under this square root, so let's square both sides, which will give us 25x squared is 9 times the quantity x squared plus 1. Let's distribute that 9 to get 9x squared plus 9 on the right-hand side. Now we'll subtract 9x squared off of both sides of the equation to get 16x squared is 9. Divide both sides by 16 to get x squared is 9/16. And of course, to get x, we need to take square roots of both sides to end up with x is 3/4. Aha! Remember what x signifies. That means that the derivative of this time function is 0 when the point to which we swim is 3/4 of a mile away from A. And when there's only one critical point like this, over the interval we care about, here as x runs from 0 to 1, we know something about what the graph of this function must look like. We don't need to know in detail, but we know there's only one turning point, as it were. It might look something like this, or it might look something like this, but there's only going to be one place where the graph turns around. At most, we could, I suppose, have a momentary flattening like we saw in the graph of y equals x cubed, but only one critical point to check. And we should check the endpoints as well, which we already did in this case, because if the graph looks something like this, then our minimum will be when x is 3/4. But if our graph happened to look something like this, then our minimum would be at some endpoint. Well, we already considered the extreme cases. When x is 0, that was when he swam straight to the shore and then ran over in 32 minutes. And the other extreme case, when x is 1, when he swam all the way to the shore in a little more than 28 minutes. So let's just see how much time it would take him to follow the particular path here. So if he follows the path where x is equal to 3/4, which would look something like this, he'll reach the treasure in, well, how many minutes? Well, that's what our function t does. It gives us the time it takes. So t of 3/4, well, we just go up here where we've got t as a function of x. And popping 3/4 into that thing, we get a third of 9/16, that's the square of 3/4, plus 1, plus a fifth of 1 minus 3/4. Well, 1 is 16/16, so you add on 9/16 and you get 25/16. You take the square root of that and you get 5/4, like so. And when you multiply these fractions together, you end up with 5/12. Meanwhile, over here, 1 minus 3/4 is, of course, 1/4, so this multiplication gives us a 20th. And the units here for time are hours. So let's see, 5/12ths of an hour. 12 goes into 65 times. So each 12th is 5 minutes. That means 5/12ths is going to be 25 minutes. And a 20th of an hour, well, that's 3 minutes. So 25 minutes and 3 minutes gives us a total of 28 minutes on the nose. Ah, that is faster than swimming straight from P to R, which was 28 minutes and a few seconds. Which means that our graph, rather than looking precisely like one of those, would be more like this. The time is shorter when x is 1 than it is when x is 0, but it's shortest of all when x is 3/4. This is the fastest route for the pirate to take. And we are done. And that means it is time to move on to our next example, our third. And for this one, I'll give you an example in which we can see a few variations on our theme. Of all isosceles triangles whose equal sides are 3 units long, the one with the greatest area is the right isosceles triangle. Explain why this is so. So we're given this assertion, this geometric fact, and we're asked to prove it. And this all has the flavor of optimization because we are talking about finding a shape with the greatest area given certain constraints, namely that we're working with isosceles triangles. And as always, let's screw around with the problem a bit just to get a feel for it. We're talking about isosceles triangles, all different varieties whose equal sides are 3 units long. So we could be looking at triangles like this, or this, or this, or even very special isosceles triangles like this equilateral triangle, or this isosceles right triangle. And of course, there are infinitely many other versions we could have. But the claim here is that of all of the infinitely many possibilities, the one whose area is maximized will be this one, the right isosceles triangle. And we need to prove this. And do not be put off by the scary word prove, because this turns out to be a sort of proof by calculation. We just have to set the thing up in the right way. What really differs amongst all these various triangles? Well, it's really just the angle between the two equal sides. It's bigger in some cases and smaller in others. So let's just draw one general picture to cover all the cases. Here it is, and I will label this angle alpha. This angle alpha could be anything from 0 up to pi radians. In both of those extreme cases, the triangle would disappear. If we're very close to alpha being 0, we would get this long, skinny triangle like that. So we would say that if alpha actually was 0, we would have no area at all. And similarly, if alpha approaches pi, we would have this other very long, skinny triangle like that with a small area. And when alpha actually got to pi, we would have no area whatsoever. If we sketched out a graph of area as a function of alpha, we know we'd have these 2 points, and everywhere in between it would be positive. Now we're not sure what it looks like. Maybe it just goes up and then comes down, or maybe it wiggles around a little bit, and there are various local maxima. We'll determine that soon. But one thing that is going to help us, since we're trying to maximize area, is to write down an expression for area in terms of alpha. That's going to be the first thing in our solution. So how do I do that? Do I have enough information here to give me the area of this triangle as a function of alpha? We do. There's a quick way to get the area of a triangle when you know 2 sides and its included angle. You might have learned that in a trigonometry class, but in case you haven't, let's just get this by going back to a formula that everyone knows. Everyone knows that the area of a triangle is half its base times its height. And those are things we can come up with pretty easily by thinking about our picture. When we drop that perpendicular, the symmetry of the isosceles triangle tells us that we actually bisect that angle right there. So that this little angle right here would be alpha over 2. And now I have a right triangle where I know the hypotenuse and I know one of the acute angles. And so as you learned very early in trigonometry, we can write down expressions for the 2 legs of that right triangle very easily. This one, the one opposite that angle, is of course 3 times the sine of alpha over 2, while this one, the leg that is adjacent to angle alpha over 2, will be 3 times the cosine of alpha over 2. And thus, the area of our isosceles triangle, half the base times the height, well, here's half the base, and here's the height. And if we multiply those 2 together, we get 9 times sine of alpha over 2 times cosine of alpha over 2. Well, this is a great start. We have an expression for the area of the triangle in terms of alpha. And at this point, you might be tempted to excitedly start taking derivatives and so on and so forth, but don't do that just yet. As I have said before, if you have the opportunity to simplify a function before you take its derivative, do so. It will save you a lot of headache later. Well, can I simplify this thing? We certainly can if you know your basic trig identities. In particular, if you know the double angle identity for sine, which you should know. The sine of 2 theta for any theta is 2 sine theta cosine theta. It's a hard one to forget because it's so musical. 2 sine theta cosine theta. It sounds like a line of poetry. Anyway, if that is firmly in your head, as it should be, then when you see this expression with the sine of something cosine of something, that should remind you of, oh yeah, 2 sine theta cosine theta. Never mind that I have alpha over 2 instead of theta. Theta can represent anything here, including alpha over 2. And you might say, but I don't have that 2, I've got a 9. Well, that's easily fixed, because we can just rewrite this 9 as 9/2 times 2. And now I've got 2 sine something cosine something, and our identity tells us that 2 sine something cosine something is sine of double that something. So all this stuff, 2 sine something cosine something, is sine of double that something. In other words, it's sine of alpha. So all this just becomes sine of alpha. And now we have a really tight expression for the area of that triangle. Much nicer than it was before. In fact, this is so nice that we can understand why the right isosceles triangle gives us the maximum area without doing any calculus at all. And that's one of the reasons why I wanted to show you this problem, that you don't always need calculus to optimize. The reason why it's easy in this case is because the function is so simple. The 9/2 just sits there while all the action is undertaken by sine. Well, what is the largest that sine of alpha can ever be? Of course, the largest it can ever be is 1. That's the maximum value of the sine function. And when does that happen? What does alpha have to be for sine of alpha to be equal to 1? Well, this is obvious. Just think about the unit circle. Sine, the second coordinate, is 1 when the angle is pi over 2, when we have a right angle. So it would be perfectly legitimate to follow this simply by saying, which is obviously maximized when alpha is pi over 2. And that would be the end of the game. That's definitely the nicest proof. But let's pretend for a moment that we didn't notice that, which would be unfortunate, and we wanted to do it with calculus anyway. So if we're going to use calculus to maximize this thing, we want to think about hilltops, places where the derivative is 0. And we're hoping we have such a hilltop on this graph somewhere. And in fact, we're hoping it occurs right here, midway between 0 and pi, so that we get pi over 2. How do we locate such hilltops? Well, of course, we figure out where the derivative is equal to 0. So we're going to need to take the derivative of this thing, which is really easy. The derivative of 9/2 sine alpha is, of course, 9/2 cosine alpha, which is 0 when, well, in your mind's eye, you picture the unit circle. Cosine is the first coordinate. So over here, cosine of 0 is 1. When does the first coordinate get to 0? Well, over here, when the angle is pi over 2. So that happens when alpha is pi over 2. This is the only critical point between 0 and pi. That means there's only one turning point. And there has to be a turning point. It can't be like one of those x cubed guys, because we start at 0 and end up at 0. So we must go up and come down. And it happens at pi over 2. Thus, the maximum area occurs when the triangle is a right isosceles triangle, as claimed. And the graph looks something like this, which of course is actually obvious all the way back here. You could have just thought of the graph of this thing and solved the problem that way too. Good, wasn't that nice? After 2 long problems, you expected the third example to be even longer, but no, it was short. But note how much shorter it was by doing that initial simplification, and that involved trigonometry to get the area down to something as simple as this from something as nasty as 9 times sine of alpha over 2 times cosine alpha over 2. Always take the time to simplify your functions when you can. Know thy trigonometry. It's important. There's another point I want to make that I alluded to in the previous video, and this problem is probably a good place to make it. As you've seen in these examples, just by thinking it through, we can usually figure out whether something has to be a maximum or a minimum. But if you weren't very good at that, if you were just a computer and had to have these things programmed explicitly into you, one way you could distinguish a local maximum from a local minimum without having to actually see pictures is by thinking about the second derivative at such a point. Any local maximum is going to be concave down in a neighborhood of that point. That means the second derivative will be negative there. Any local minimum is going to be concave up in the neighborhood of that point. That means the second derivative is going to be positive there. We went over all that at the beginning of the previous video. That means if I'm operating blindly and can't think my way through something to see whether it's a local maximum or a local minimum I'm dealing with, I could go to the second derivative and figure it out mechanically. Like in this case, I found my first derivative, I set it equal to 0, and I found I only had this one critical point. Now, the function I was dealing with was so simple that it was obvious that I had a maximum there. But if I'm just a computer, and I don't know these things, and I can't see pictures and can't think geometrically, I might want an algorithmic way to figure it out. Well, one thing I could have done is use this so-called second derivative test. Here's my first derivative. I could take the second derivative as well, which in this case is mercifully easy, because if the first derivative is 9/2 cosine alpha, then the second derivative is minus 9/2 sine alpha. And if I was interested in what's going on at this critical point, where alpha is pi over 2, then I could just look at the value of the second derivative at pi over 2, which is minus 9/2 sine of pi over 2. And of course, sine of pi over 2, well, thinking about our unit circle, that's going to be 1, which means that this factor can just be erased. So the second derivative is negative. A negative second derivative corresponds to concave down. It's this case, which means that we must have been looking at a local maximum. So the critical point at pi over 2 is a local maximum. Now, truth be told, in most cases, the second derivative of the function you're working with will be so ugly that you probably won't want to go through with the second derivative test. But you could try it, like in the previous example we did with the pirate, compute the second derivative of the time function at our one critical point that we found, and you'll find that its value will be positive, meaning that we were looking at something concave up, meaning that we had a local minimum, because he was trying to minimize time. Anyway, it's worth knowing about this second derivative test, even if we don't use it all that often, because you will see versions of it when you get to multivariable calculus. And in some ways, everything we've done in this lecture is really pointing towards multivariable calculus, calculus of several variables. Because if you have a function not just of one variable like this, but a function of 2 or more variables, you can't solve the problem just by graphing it and looking to see where the hills and valleys are. I talk about this a little more in the book, especially if you're working with a function of 3 or more variables, because then your graph would require 4 or more dimensions, which is obviously something you can't see. But it turns out that when you do differential calculus in that setting, you still have some analog of a second derivative test that you can use. It's more complicated than anything I can talk about here, but all this stuff carries over very nicely into places that you can't actually see. So you want to get used to the ideas here, where everything is much more tangible. And when you eventually get to the point where you're taking multivariable calculus, and you have all these second partial derivatives flying around, you still want to be able to think about the fairly humble ideas we've been talking about here. The connection between second derivatives and whether something is concave up or concave down. The idea that we try to find local maxima and minima by seeing where a derivative is equal to 0, which corresponds to a horizontal tangent line. In multivariable calculus, you'll be looking at things like horizontal tangent planes if you have a function of 2 variables. And if you have functions of 3 or more variables, you would have things like horizontal hyperplanes for what that's worth. But you'd still be looking at where some analog of the derivative is equal to 0. So everything you're learning here will serve you in good stead as you move into more complicated courses, such as multivariable calculus, where you start to reach techniques that connect very nicely to how things actually operate in the real world, because many of the functions we're interested in the real world aren't just a simple function of one variable. If we're trying to maximize profit, there's generally more than just one variable that the profit depends on. There might be 5 different variables, or 20 different variables. But to understand how to do calculus in those settings, you first have to understand how to do it, and above all, how to think about it in these simpler settings. So, this has been a long one, so I'm going to stop here and let you get to the homework problems. I hope you'll find some of them accessible and some of them quite challenging. And of course, be sure to read the corresponding section in the book. I have a few more examples there. As I have said before in these videos, videos are not replacements for the book. They just supplement what's in the book. In the book, I can be careful about what I'm writing, and then go back and edit, and so on and so forth. On video, well, I'm mostly sort of speaking off the cuff, as I would when giving a lecture in a classroom. You want both presentations. Anyway, enough is enough. This has been a long video, and it's time for me to go eat dinner. See you next time.